Hello and welcome to this session. In this session we are going to solve one physics problem related to radioactive decay process, and this problem is from one of the past JEE advanced papers. So let us first go through the problem statement. For a radioactive material, its activity A and rate of change of its activity R are defined as A equal to minus dN by dt and R equal to minus dA by dt, where N of T is the number of nuclei at time t. Two radioactive sources P with mean life tau and Q with mean life 2 tau have the same activity at t equal to 0. Their rates of change of activities at t equal to 2 tau are Rp and Rq respectively. If Rp by Rq equals N by E, then the value of N is what? Okay, so now let us take a look at what is given and what we need to find. So it is defined that the activity A as minus dN by dt and the rate of change of activity as minus dA by dt. So what is this activity? So you can see here dN by dt is the change in number of nuclei with respect to time. That is the first derivative of N of t. Okay, N of t is the number of nuclei at time t, right? Now why we have this negative sign here, that I will explain towards the conclusion of this video. For now let us take the definition as it is. So activity is defined as minus 1 times the first derivative of N of t, and the rate at which this activity changes, that also equal to minus 1 times dA by dt. Okay, now what about this N of t? N of the t is the number of nuclei at time t. So for a radioactive material, we know this equation N of T equals N of 0, that is the number of nuclei at time t equal to 0, into e power minus lambda t, where lambda is the decay constant, right? Okay, so given this N of T, we can find A and R. Now there are two radioactive sources, one labeled as P, another one as Q, and P has a mean life tau and Q has this mean life 2 tau, and both of them have the same activity at t equal to 0. So what does it mean? Activity is the minus times the first derivative of N of t. So let's write the mathematical equation for this. Let us say Np of t is the number of nuclei for source P. We will use different notation for P and Q because both are two different radioactive sources and both of them have different mean life. So let us use different notations, and Nq of t is the number of nuclei for source Q at a time t. So what is AP of t equal to minus, this is the first derivative, right? Np of t. Let me use this notation for derivative, and likewise here Aq of t equal to minus Nq of t, first derivative. And what they are saying is at time t equal to 0, both have the same activity, that is AP of 0 is same as AQ of 0, right? The activity at time t equal to 0 for source P and the activity at time t equal to 0 for source Q are equal. And then their rates of change of activities, that is R, at t equal to 2 tau or Rp and Rq respectively. So Rp of t is the rate of change of activity for source P equal to minus d AP by dt. Likewise here Rq of t equal to minus dAq by dt, and the value of this function at time t equal to 2 tau, right? So the ratio of these two values, that is Rp of 2 tau by Rq of 2 tau, is given as N by E, and we are required to find N. Okay, so we have N of t and we know AP of t, that is the activity for source P, equal to minus first derivative of N of t for source P, likewise for source Q also, and Rp of t, Rq of t is defined. Okay, and given this ratio we need to find N. Okay, so now how we are going to approach this problem? So first thing is we need to find this one. Rp of t and Rq of t, and here we can substitute t equal to 2 tau and find this ratio and then equate that to n by e, and we can see whether we can evaluate the value of n from there. So let us start with finding Rp and Rq at time t. Rp of t equal to minus, we need the derivative, sorry, we need ap of t, right? So let's first find ap of t. Ap of t equal to what? Minus first derivative of np of t. So what is np of t? Np of t equal to the same equation, but we use different notation for source p and source q. So lambda p is the decay constant for source p. Now in the problem they have not given this decay constant for source p and q, right? But they have specified the mean life. So what is the relationship between the decay constant and the mean life? Decay constant is nothing but the inverse of mean life, right? So that means 1 by tau is the decay constant for source p. We can use this. So now first we need to find this ap of t is minus first derivative of np of t. So if we take the derivative of this one, what we are going to get? Np of 0 e power minus lambda p t. See, if we differentiate e power ax with respect to x, where a is a constant, then we are going to get a into e power ax. That is the original function multiplied by this constant a. So likewise here, minus lambda will come here, so this becomes plus lambda, and the original function, that is np of 0 into e power minus lambda p t. Okay, this is ap of t. Now rp of t is minus time derivative of this one, right? Minus derivative of a of t. So this is lambda p, and here again np of 0, this minus lambda p will come here, so that means plus lambda p square e power minus lambda p t. This is rp of t, that is the rate of change of activity for source p at a given time t. Now here we can substitute t equal to 2 tau, that is rp of 2 tau equal to lambda p. What is lambda p? 1 by tau, right? So 1 by tau square np of 0 e power minus lambda p into t. So lambda p is 1 by tau, and time we are substituting 2 tau, right? So 2 tau. So that means tau gets cancelled. In the exponent we have minus 2. So we got the value for rp of 2 tau, right? Likewise we need to find rq of t. So first let us write nq of t equal to nq of time equal to 0 e power minus lambda q into t, and then aq of t equal to minus time first derivative of this one. That means nq of 0 e power minus lambda qt, and this minus lambda q comes here, and the second derivative, that is rqt equal to minus derivative of this one. So lambda q nq of 0 e power minus lambda qt, this minus lambda q comes here, so plus lambda q square. And lambda q, what is the decay constant for source q? That is the inverse of mean life. Mean life is 2 tau, right? So that means lambda q square is 1 by 2 tau whole square, that is 1 by 4 tau square. And nq of 0, what about the exponent? Lambda q into t equal to 1 by 2 tau. Before that, okay, yeah, we need to find rq at t equal to 2 tau, right? Yes, so this is rq of t, this we already found. Now we are going to find the value of this function at t equal to 2 tau. So that means the exponent here will be 1 by 2 tau into time t equal to 2 tau. So both get cancelled. In the exponent we have minus 1, right? So we have this one also. So we have rp at 2 tau and rq at 2 tau. Okay, now we can find this ratio. So rp at 2 tau divided by rq at 2 tau equal to 1 by tau square np of 0 e power minus 2 we can bring it to the denominator into inverse of this one, that is 4 tau square by nq of 0 e power minus 1 we can move to the numerator e. Now tau square cancels this e, okay, just let's write 4 np of 0 by nq of 0, 4 we have written, np of 0 nq of 0 we have written, e by e square is 1 by e. Okay, so now we have found this ratio also, and this is given in the problem as this is equal to n by e, and we are required to find n, right? So let's write it here, or p at 2 tau by or q at 2 tau equal to 4 times 4 by e times np of 0 by nq of 0, and this is given in the problem as n by e. That means n equal to, e gets cancelled, 4 times np of 0 by nq of 0. So we have almost solved the problem. Now we only need this ratio, the ratio of the number of nuclei in source P at time t equal to 0 to the number of nuclei in source Q at time t equal to 0. So how can we find this one? Have they mentioned anything about the number of nuclei in source P and Q? No. But only thing they have mentioned is both of them have the same activity at time t equal to 0. That is, here we have written, right, AP of 0 equal to AQ of 0. And we know AP of 0, we know AQ of 0. From this derivative we can find, right? So one thing is, see, here it is AP, right? If you substitute, you see in this equation, this contains this term, this factor np of 0, AP of t. Likewise, AQ of t contains this factor nq of t. So that means if you take the ratio of both of these, then you can get np of 0 by nq of 0. And they have given both are equal at time t equal to 0, right? So the value of this function and this function is same when t equal to 0. So you can substitute t equal to 0 here and here. So that means this exponent e power 0 become 1. So this will be trivial and we can ignore this factor. Likewise here also, if t equal to 0, then this entire factor becomes 1. So you can ignore that one. So that means only thing, lambda p and lambda q will remain, and we have np of 0 and nq of 0. So we can try to use this condition. So ap of 0 equal to lambda p np of 0 e power 0 equal to 1, right? So becomes 1. Likewise aq of 0 equal to lambda q nq of 0 into 1. Lambda q nq of 0, anything for 0 is 1, right? Now if you equate both of them, ap of 0 equal to aq of 0 is given in the problem, right? So this implies np of 0 lambda p np of 0 equal to lambda q nq of 0. Okay, now we can get this ratio from here. So np of 0 by nq of 0 equal to lambda q by lambda p equal to what? Lambda q, we already noted that 1 by inverse of the mean life period. Lambda p equal to 1 by inverse of the mean life period. Here itself we have written lambda p 1 by tau and lambda q 1 by 2 tau. So this is 1 by 2 tau into tau equal to, tau gets cancelled, 1 by 2. Okay, so that means n equal to 4 times, this ratio is 1 by 2, right? 4 times 1 by 2 equal to 2. So n equal to 2 is the solution for our problem. Okay, now let's take a quick look into what we have done. All that we have done is just we rewrote the same equations definitions for source P and source Q. Okay, AP of T equal to minus first derivative of N of T, likewise for Q, and RP of T equal to minus first derivative of AP of T, likewise for source Q. And we noted this equation N of T. This is the equation that describes the radioactive decay process, and it gives the number of nuclei at time T, and that is equal to number of nuclei at time T 0 into e power minus lambda T, where lambda is the decay constant for that particular radioactive material. Now, since we are dealing with two different sources having different mean life period, we need to use different notations for NP of T and NQ of T. Okay, all that remains is to find the derivatives. The first derivative to get AP of T and the second derivative to get RP of T. And we found those derivatives and we substituted T equal to 2 tab for RP and RQ, and we found that ratio and we equated it to the given value N by E, and here we found that N equal to 4 times this ratio. So for this ratio we use the other condition, same activity at T equal to 0. That means AP of 0 and AQ of 0 are equal, and we noted that AP of T contains this factor NP of 0 and AQ of T contains this factor NQ of 0. So we made use of this condition and substitute T equal to 0 in both these equations and got the ratio and equated to 1, and we got N equal to 2. Okay, now before we conclude, let me quickly explain why we have this negative sign here and here. So dN by dt, so let's consider radioactive material. Let's say there are n number of nuclei, and after a time period equal to the half-life period of that radioactive material, half of this will decay, right, over a period of time which is equal to the half-life period of this radioactive material. Half of this nuclei will decay and remaining will be n by 2, right? So n by 2 will decay and n by 2 will remain. Now you see this dN by dt is going to be negative always, because the number of nuclei is decreasing with respect to time, and that too exponentially decreasing. Okay, so that's why we always have dN by dt is less than 0. Now the reason why we define activity as minus dN by dt is activity is actually the number of decaying nuclei, that is the decreasing nuclei, that is the decreasing nuclei with respect to time. Why we are interested in this quantity is because this activity is used to measure the radiation. So the number of decaying nuclei, right, so they are the ones that contribute to the radiation. So in this, let us say for example, let's say there are like 10,000 nuclei, okay, and over a period of time equal to the half-life period, 5,000 will decay, right, and remaining will be 5,000, and this 5,000 decay nuclei, right, they are the source of radiation. Okay, so that's why we are interested in the number, not in the negative sign, because change means it can be positive, negative, and in this case it is negative, it is less than 0. Change means we will get minus 5,000. Okay, but we are just interested in the absolute value. So we can also define A equal to mod of dN by dt. That is also a valid definition. Okay, so since we are only interested in the number of nuclei decaying, that is decreasing nuclei, decreasing quantity, that's why we have this negative sign. Similarly for this rate of change of activity also. Okay, I think with this we can conclude this session, and I hope this session helped you in your learning, and we will meet again in another video. Thank you.